Okay, AP Chem. In this video, I'm going to quickly go through some Gibbs free energy concepts that you have to know for the end of this unit, and then we're done with the unit. We won't go through some other details of Gibbs free energy. We're just going to use these two equations in this unit. AP Chem goes beyond that, but at this point, we'll just wrap this unit up, kind of shorten it, and then we'll go into reviewing. So in this video, I'll review how to use these two equations. This first one for Gibbs free energy, any temperature, and this one at standard temperature. And this will give you the information you need to be able to answer the questions in the Gibbs free energy concepts worksheet that you have. If you were here before break and didn't miss the 2 days before the closure, you probably know enough information to be able to answer all the questions in the Gibbs free energy concepts worksheet already. But if you don't, this will be a review for you. Before we do that, I want to review some concepts of the unit. So there's 4 statements here, and you can pause the video and see if you can answer this. Explain why each of the following statements are incorrect. So go ahead and pause it. And I'll answer these questions for you here. Hopefully you got this for number 1. Entropy increases in all spontaneous reactions. It's incorrect because it's not the entropy of just the reaction. You'd have to say entropy of the universe. If you said entropy of the universe here, then this would be a correct statement. All spontaneous reactions have an increase in entropy of the universe. Number 2 says reactions with a negative free energy, that's Gibbs free energy, delta G, less than 0, are product favored. This is true, they are product favored. And occur with rapid transformation. This is saying the rate of the reaction. Well, Gibbs free energy does not tell us the rate of a chemical reaction. They're independent of one another. So the first part of this statement is true. They are product favored. But the rapid transformation, you cannot determine whether the reaction is quick or slow based on the Gibbs free energy. So this statement would be false. You'd have to remove that last part of it. 3 and 4 are directly connected to each other. 3 says all spontaneous processes are exothermic, and 4 endothermic processes are never spontaneous. If you were here the last 2 days before break, we looked at this equation here for calculating Gibbs free energy. If we want a spontaneous process, we want the Gibbs free energy to be a negative value. And if we evaluate this equation here, number 3 says all spontaneous processes are exothermic. If we can answer number 4, we'll be able to answer if number 3 is correct. Endothermic processes are processes where your delta H is positive. And if delta H is positive, the question is, can our Gibbs free energy here ever be negative? If it can be negative, then we have a spontaneous process with a positive delta H, which would be an endothermic reaction. And the answer is yes, you can. You can have a negative delta G as long as the delta S for the process, or the change in entropy, is also positive. That would mean the process would have to increase in entropy or increase in disorganization. If this is the case, if both are positive, then you can end up with a negative as long as this term is a larger quantity than our delta H. And for that to happen, this would happen at high temperatures. So to get a large number here, we want high temps. And so number 4 is incorrect. These can be spontaneous at high temps, only at high temps. And high temps is relative. It could be temperatures above 10 degrees Celsius. It could be temperatures above 1500 degrees Celsius. It just depends on how large delta H is and the size of delta S, which means number 3 is incorrect. All spontaneous processes are exothermic. Well, number 4, we just described an endothermic process that is spontaneous, and that's why number 3 is incorrect. So that's a little review for Gibbs free energy and how it relates to entropy. Let's talk a little bit about how we calculate Gibbs free energy. These equations should look familiar to you. We used these for our enthalpy, and the little symbol here, this is your standard state, and for a standard state for thermodynamics, that's 25 degrees Celsius, 1 atmosphere pressure if you have gases, and 1 molar concentration if you have solutions. And so if we want to calculate the change in heat, we do sum of products minus reactants. Change in entropy, same equation. Gibbs free energy, same equation. And we did this in class. If you're given the S values, the entropy values for a chemical reaction, you can do sum of the products minus sum of the reactants. Just remember, if you have certain moles greater than 1, you need to multiply that in your equation. So the H2 here, the 130, it's going to be doubled, and my H2O is also going to be doubled right here when we plug it into our equation. This will be on your AP test, mainly with the delta H up here, because this is in a unit that you're not going to see a lot of questions on the AP test. So you're going to use this on the AP test. Remember how to use those guys. That works for Gibbs free energy as well. So I want to just talk a little bit about what does this Gibbs free energy actually mean, and what's the difference between the standard condition Gibbs free energy and Gibbs free energy at any other temperature. So here's a chemical reaction. They give us the Gibbs free energy. It's a negative value. It's already been calculated for us. And this negative value indicates that this particular reaction is spontaneous in the direction it's written at these temperatures. This would be at 25 degrees Celsius and at a pressure of 1 atmosphere for all of our gases. So that means I would have a container with 1 atmospheric pressure of this, 1 atmospheric pressure of this, and it already has some of our product here, 1 atmospheric pressure of this. And that means our chemical reaction is going to proceed in this direction if you have a container with a little bit of, or equal amounts of all of these gases in the container for 1 atmospheric pressure. That's your partial pressures of all these gases. So this would be a product-favored reaction. It would be spontaneous, and this combustion of methane, which happens to occur with the Bunsen burner, and we know that once you start that reaction, it continues to occur, and that's what spontaneity means. So what does the little symbol here mean? It means that we're calculating it only for this condition, 25 degrees Celsius, 1 atmosphere, or for solutions 1 molar. So if you're doing this equation, that's your specific scenario. If you're going to use this equation, this allows you to calculate your Gibbs free energy at any temperature. And as temperature changes, these two terms actually do change. The delta H and delta S do change at different temperatures. And because of that, this is an estimate. We estimate this. If we use our delta H here at standard and our delta S at standard conditions, we're doing an estimate for a Gibbs free energy at that new temperature. So all that is saying we can have different temperatures here and get a different number for our Gibbs free energy if we're not at 25 degrees Celsius. So that's the difference between this equation and this equation. They're just for calculating Gibbs free energy at different temperatures for the same chemical reaction. That's it. Another way to think about Gibbs free energy as it relates to a chemical reaction is its equilibrium position. So we said that this particular reaction, because it's a negative Gibbs free energy, this is a product favored chemical reaction. Product favored means that your K value for the reaction is going to be greater than 1, much greater than 1 in this case. And that means if I let this chemical reaction, if I start with 1 atmospheric pressure of all of these, and I start the chemical reaction, I light this on fire, it's going to go to the product side to establish equilibrium by producing a lot of products and very, very little reactant left over at the end. When we're at equilibrium, we know that the equilibrium value for Gibbs free energy is 0. So this reaction will progress forward. This will decrease in pressure, and this will increase in pressure until my Q value for the reaction equals my K value. And when your Q value equals your K value, if you remember from your equilibrium unit, this is when we're at equilibrium. And for this reaction, it would be almost no reactants in all products. At that point, my Gibbs free energy would change values, and it would become a 0 kilojoules per mole, even if it's still at 25 degrees Celsius. So this particular calculation for Gibbs free energy, this is for standard states. You have to have the 1 atmosphere. We're not looking at the chemical reaction at equilibrium already. So one of the ways to think about that, all chemical reactions try to tend to go to equilibrium position. And if you look at a little curve right here, that means if my Gibbs free energy value is not 0, the reaction, in this case, we have a negative Gibbs free energy, we're on this side of it, the reaction is trying to go towards this 0 Gibbs free energy. And when it's at this Gibbs free energy of 0, the chemical reaction is at equilibrium. If we calculated our Gibbs free energy for this reaction and we got a positive value here, all that means is we're not at equilibrium and the reaction is non-spontaneous in the forward direction, but it would be spontaneous in the reverse direction. So if we got a positive value, we would say this reaction is going to go this direction to reestablish equilibrium. And that would look like this. We'd have a Gibbs free energy here and it'd start going towards equilibrium, and it tries to get my lowest Gibbs free energy for that particular reaction. All it's saying is we're trying to reach the lowest energy state for every chemical reaction. So it's related to equilibrium. We won't go into this part. This is the additional part of this unit that we aren't going to look at. It's not going to be part of your AP test. but Gibbs free energy is related to equilibrium position, and there's lots of applications for this. But I just wanted to show you that conceptually so you can get an idea what's the difference between these two Gibbs values. The difference is that we're at different temperatures, and at different temperatures you're going to have different Gibbs free energy values, but you also can change your concentrations and get different Gibbs free energy values. We will not do any calculations at different concentrations. Both of these are assuming that your concentrations are 1 molar and your pressures are 1 atmosphere for your gases. The only difference is temperature between these two equations for Gibbs free energy. Yeah. So every chemical reaction does have a point. Well, not every chemical reaction has a point where Gibbs free energy is 0. Some chemical reactions will not. So if we look at this equation here, these are the values if you missed the 2 days before break. This is what your Gibbs free energy means. You might take a second, read through those, and write that down. If you want to calculate Gibbs free energy for a problem, if they give you the actual Gibbs free energy formations for a particular reaction, you can plug those in, do products minus reactants, and we get a slightly different value than I have on the last screen here. These values would be from different tables, but this one comes out to negative 800. This is the same chemical reaction that we were looking at earlier that was negative 18 kilojoules per mole, but we'd have a spontaneous reaction here. And this is a pretty simple calculation. So if you have a problem that asks you just calculate Gibbs free energy at standard conditions, that'd be your standard free energy, just do sum of products minus sum of the reactants, and you have to look those up on the table. This one asks you to use the standard enthalpy. This is delta H, so another type of problem here. Standard enthalpy would be delta H, and your standard entropy to calculate the change in Gibbs free energy. So for this particular problem, you would be thinking, I am not going to be given the Gibbs free energy formation values, so I can't use this first equation here. I need to use this equation. My Gibbs free energy equals my change in enthalpy minus temperature times my change in entropy. And these values you'd have to calculate for this particular problem, and then plug in our temperature. This is another indication that we can't use the first equation. The first equation is only for 25 degrees Celsius. And since we're not at 25 degrees Celsius, we have to use this equation. And temperature needs to be converted to Kelvin. The other thing you want to think about when you use this equation is the units for enthalpy are generally given off of your thermodynamic value sheet as kilojoules per mole, and the units for your entropy are usually in joules per mole times Kelvin. Well, the kelvins will cancel, but the joules up here, you can't add a kilojoule and a joule or subtract them. You have to be in the same units, and I like to divide the entropy by 1,000 every time to convert into kilojoules per mole. And then my answer for Gibbs free energy will be in kilojoules per mole as well, but the units are not the same for these. So if you walk through this problem, we would look up all these values, the enthalpy values. These are the standard enthalpies of formation for all of these compounds. I'd look up the entropy values for all the compounds. They're in joules per mole, and we're in kilojoules per mole for our enthalpy. And then with our balanced equation, we'd multiply everything by the correct number of moles, sum of the products minus sum of the reactants, and we get our enthalpy change for the reaction. This would be an exothermic chemical reaction. And our entropy change for the chemical reaction, it's negative. That means our entropy decreases, and it's saying we get more organized. And that makes sense if you look at your chemical reaction. We go from 7 moles to 2 moles, and we go from gases and some solids to all solids. So we're getting more organized here, and these two numbers match with that. You'd plug those into your Gibbs free energy equation. In this case, I converted kilojoules to joules, so we went into millions of joules. Temperature for the reaction was 156 degrees Celsius. Convert 156 to Kelvin, add 273.15, and plug it in for a temperature. And then we plug in our change in entropy, which is in joules per mole times Kelvin. If you plug that into your calculator, you get this, negative 1.42 times 10 to the 6 joules per mole, or negative 1,400 kilojoules per mole. So this would be a very spontaneous reaction, very product favored. And we know that it's spontaneous because this is the formation of rust. And this spontaneously occurs on all iron exposed to oxygen. It's happening on your car as we speak. So can an endothermic reaction be spontaneous? We answered that earlier qualitatively, but let's look at one of these reactions with some numbers with it. This is a chemical reaction of barium hydroxide with It's a hydrated compound with 8 H2Os. You can react this with ammonium chloride. If we were in school, I'd show you this demonstration. It's a very, very cold chemical reaction. It's very endothermic. And the particular reaction produces a gas, liquid, and a solid. So if we just want to predict our signs here, you should be able to do this at this point in the unit. What's the sign of, we already said it's endothermic, so what's the sign of delta S for this reaction? Well, the sign for delta S is going to depend on your organization. So let's look at our organization. The first thing I want to know is what's our states of matter on this side. And on this side, we're all solids. And on this side, we have some gas. Here's our gas and a liquid and solid. So just looking at states of matter, we would say we're going from the most organized state to some of the least organized state and a little bit of our in-between, our liquid state. So we're getting less organized in terms of states of matter. And then if we look at the number of moles, on this side we have 1 mole plus 2 moles, we get 3 moles of solid. And on this side we have 2 moles of gas, 10 moles of liquid, and 1 mole of solid. So total moles on this side, we go from 3 moles to 13 moles. So we're getting less organized by number of moles and by the states of matter. So we'd say we're getting less organized overall, and less organization means our entropy should increase. So this would be a positive value for our entropy. If we actually calculate those, these are standard values on a table. You could take a minute and see if you can calculate that, sum of products minus sum of the reactants. You should get these 2 values here. 164, that's our endothermic, positive. And our delta S is also positive like we predicted up there. It's 591 and we're in joules versus kilojoules. So if we want to figure out when is this reaction spontaneous, when is it non-spontaneous, we want to evaluate when the reaction is at equilibrium. And at equilibrium, our Gibbs free energy is going to be equal to 0. And if we plug that into our Gibbs free energy equation, I'm going to put in 0 for our Gibbs free energy. Our delta H is given right above, 164 kilojoules per mole, minus my temperature times, I converted to kilojoules per mole by dividing by 1,000. And if you solve for your temperature here, you get 277 Kelvin, which is about 4 degrees Celsius. So at 4 degrees Celsius, which is close to freezing, this chemical reaction will be at equilibrium. To determine whether it's spontaneous above or below that, the answer is right down here. We want to go back to our Gibbs free energy equation and plug in our values. We have a positive value, and we have a positive value here. And what that means is if we want this to be spontaneous, at temperatures where our T times delta S is large enough, this positive value subtracted from the positive value here will make this a negative value and make a spontaneous reaction. So this would be spontaneous at high temperatures. And those high temperatures are not relatively high. They're just barely above freezing. So all temperatures above 4 degrees Celsius, it's spontaneous. And all temperatures below 4 degrees Celsius, it's non-spontaneous. So the reaction would not occur without outside intervention. If you want to see this chemical reaction, I'll post a link to this YouTube video. You can watch a beaker get frozen to a board with this chemical reaction. It is very endothermic. And I'll post this link in the comments of the YouTube video for this video. I want to show you, we can skip over this one. If we look at this chemical reaction, let's just evaluate this qualitatively. You'll have problems that are like this on your test for this unit. There's no numbers given in this problem. So this is rust, iron rusting, and we just looked at that a second ago. But if you were given this problem with no numbers and you had to predict how does temperature affect the spontaneity of the reaction, or even does the temperature affect spontaneity, is it driven by enthalpy or entropy? Let's talk about what that means here. If you're given a chemical reaction like this, you should be able to predict what is delta H and what is delta S just by sign. Is it positive or negative? So I'll put my 0 here, greater than 0, less than 0. For our delta H, this one's going to take a little bit more thought than our last one. You want to think about it like this. Your oxygen, if you weren't given numbers here, your oxygen, you're breaking this bond, and you're breaking 3 of them. So I'm going to say times 3 here. There's no bonds that you're breaking here. And then you make bonds on this side. And the number of bonds that you make on this side, we have 2 irons and 3 oxygens. We're making a lot more bonds than we're breaking. We're only breaking this guy right here. And we're making bonds between a crystalline lattice structure. And I won't try to draw that out here, but each iron is going to be attached to, surrounded by all oxygens. So every single one of these atoms will have multiple attractions on the other side of it. This is a very strong bond that's being formed. So bonds breaking, this requires energy, but the bonds form is going to release energy. So we're going to release more energy here from bonds being formed than our bonds broken. And if energy is released, that means our delta H is going to be a negative value. It's an exothermic chemical reaction. And if you go back a couple slides, this one, it was an exothermic chemical reaction. For entropy, we go from a gas, 3 moles of gas, and 4 moles of solid, to a solid. The main contributing factor here, we're going from 7 moles to 2 moles. So you might say we're getting more organized with the number of moles. But there's a big change in entropy for a gas to a solid. So the primary thing you want to look at is just the state of matter here. If we go from a gas to a solid, we're getting more organized. And if you get more organized, that means your entropy change is going to be negative as well. And now we can evaluate, does temperature affect spontaneity, or how does it affect it? If this is a negative value, and this is a negative value, we want to figure out at what temperatures is this particular reaction spontaneous. And it'll be spontaneous at temperatures where this term here, we have a negative value minus negative, that's adding, so a negative plus a number. If this number is large enough, we're going to get positive Gibbs free energy changes. And so at temperatures that are high, this number, large number here, equals positive Gibbs free energy. Oops. Positive Gibbs free energy. And that number will be large when temperature is large. So at high temperatures, this particular reaction would be non-spontaneous, positive, because we have a negative value plus a large enough number. At low temperatures, this reaction would be spontaneous. So how does temperature affect it? The higher the temperature, the less spontaneous it gets. So if you don't want your car to rust, just get it at a high enough temperature. If you do the calculations here, I believe that temperature is a couple hundred degrees Celsius. So you would be destroying other things on your car, like melting all the plastics if you didn't want it to rust by getting to that high temperature. Is the spontaneous reaction driven by enthalpy or entropy? If you want it to be a spontaneous, we want this number here to be larger than our delta S. So it's driven by this number, our spontaneity is, because this is what's causing our Gibbs free energy to be negative. So we would say this is driven by enthalpy, the Gibbs free energy change. One of the last topics I want to talk about here is how does equilibrium temperatures play into phase transitions. That's going from a solid to a liquid, or from a liquid to a gas. And we're going to look at just H2O here. But for phase transitions, this is happening at temperatures other than our 25 degrees Celsius. So it's not at 25 degrees Celsius. That's going to be like for water, 100 degrees Celsius for liquid to gas, or 0 degrees Celsius from solid to liquid. So because we're not at standard conditions, we're going to use the Gibbs free energy equation like this. And for this particular problem, we're just going to look at the H2O. So from a gas to a liquid phase for H2O, what happens and what temperature does this occur at? When does H2O go from a liquid to a gas? When does it boil? Well, it's the same temperature at which it goes from a gas to liquid, and that's at 100 degrees Celsius. So we're going to get this number here using thermodynamics, not just taking a temperature probe and putting it into a pot of boiling water. So to do that, you would get your delta H. This would be your delta H for this particular process, and it'd be the standard delta H, and this would be your standard delta S for this process. To go from a gas to liquid, it's exothermic. When a gas condenses, it releases energy. And to go from a gas to liquid, we're getting more organized. And if you get more organized, your delta S would be a negative value. It's going to decrease your entropy. And so if we just look at this particular process, and we just look at the signs here, if you put in a negative value here and a negative value here, it's just like the last problem that we did. If we have two negatives, what did we say? We said to get this to be a large number and cause a positive Gibbs free energy, temperatures must be large. So at large temperatures, this particular reaction would be non-spontaneous. if you have a negative, negative. So let's look at this. Does that make sense for our reaction here, or our process? Negative, negative, this would be non-spontaneous at high temperatures. Well, at a really high temperature, are you going to get a gas to turn into a liquid and condense H2O? The answer is no, it will not. You need low temperatures for that to occur. So our negative, negative makes sense here, and that temperature transition would occur at 100 degrees Celsius. To calculate that, we just plug in our delta H here, our delta S, and we can solve for a temperature at which our Gibbs free energy is 0. Well, the temperature at 100 degrees Celsius, this is our equilibrium. We can have water in liquid state and gas state at 100 degrees Celsius. They both can coexist there. That's your equilibrium position for it. So if you plug those values in from our particular problem, I converted delta S by dividing by 1,000, and I solve for T. T will be in terms of Kelvin here. You get 370 Kelvin. Well, 370 Kelvin converted to Celsius is 96.85 degrees Celsius. And this would be where your Gibbs free energy, delta G, equals 0. Well, you might be saying that didn't work because we know that the normal boiling point for water is 100 degrees Celsius. I should get the equilibrium position for this reaction at 100 degrees Celsius, not at 96.85. Why is it not 100? The reason it's not 100 is because these values, earlier in the video I mentioned, these values actually change a little bit when temperature changes. And this is an estimate using this particular equation here of your Gibbs free energy at a different temperature because these actually change a little bit. So this estimate, we're close. If you actually wanted to get the value, you would have to measure the enthalpy change at 100 degrees Celsius and the entropy change for this process at 100 degrees Celsius, and you would get exactly 100 degrees Celsius if you use the actual values at that temperature. Okay. So if we evaluate this at a different temperature, so our gas to liquid, let's say that we chose a temperature greater than 100 degrees Celsius and a temperature less than 100 degrees Celsius, try to predict for each one of those, what would our Gibbs free energy be? Would it be positive or negative for values greater than 100? Would it be positive or negative for values less than 100? And I just chose two values here. For 150 degrees Celsius, if you plug it into our equation, our enthalpy change and our entropy, but I changed my temperature, 273.15 plus 150 degrees Celsius, you get a positive value. That would mean that it's non-spontaneous at temperatures above 100 degrees Celsius. And for this reaction at temperatures above 100 degrees Celsius, we're not going to get gas to a liquid. And for temperatures below that, if you plug it into your equation, we get a Gibbs free energy that's negative. And that would say that our process is spontaneous. We're going to spontaneously have the gas turn to liquid at temperatures less than 100, so at 30 degrees Celsius, you would for sure see H2O gas turning into a liquid. And that's how your Gibbs free energy can help you with phase transitions. You can predict what temperature that phase transition should occur at. If you summarize this in a table on the Friday before we left for the closure, I summarized this on a little table here. There's only 4 types of chemical reactions. There's chemical reactions where your delta H is positive and your delta S is negative. This would be an endothermic chemical reaction that has a decrease in entropy, so it gets more organized. For these particular reactions, if this is positive and this is negative, a positive minus a negative, that's plus, so a positive plus a number will always be positive. So these ones are always non-spontaneous reactions. If you have a reaction that has a negative and a positive, so I have a negative for delta H and a positive here, well, a negative number minus a positive number will always give me a negative Gibbs free energy. This will always be a spontaneous reaction in the direction it's written. Once you get started, it'll continue to go, and it'll always be product favored. If you have these other 2 special cases at the bottom, we looked at the negative negative already in this video. Let's just look at the positive positive. If we have positive here, if we want this to be a spontaneous reaction, we want this positive value to be subtracted by a large enough number, this needs to be large, so that we get a negative Gibbs free energy. How do I make this large? I need high temperatures. So at high temperatures, we're going to have a spontaneous reaction. And at low temperatures, if this is a small number, our positive value minus a small enough number will remain positive, and it'll be non-spontaneous. So those are your 4 types of reactions with Gibbs free energy.